Welcome to your week 4 video for NUC 110. Here are your assignments that you'll find under coursework on Blackboard. I want you to take a look at the test number 1 key, which we're going to look at now. Look at the control rods and the nuclear fuel power points, which we will also do now. And then define these terms. So it looks like I've got 6 terms there. Just define those and email them back. Explain the purpose of each of these 7 HCU headers. There they are. And just tell me what each one of those does. And then there are 2 videos to watch, but you don't have to write a paper or anything like that. So just both those videos will help a lot with your understanding of the material. So please do take a look at those. So let's quickly go through the key. PWRs are operating around 2,250 pounds. BWRs are around 1,000 PSI. Boron is injected in a boiling water reactor only for emergencies, only when we're in the end times. So water is going to be our coolant for all of our American nuclear reactors. There are other coolants possible, but water is the one that we will use here. And all commercial power plants are going to use steam to spin a turbine. So nuclear plants do not start up and shut down frequently, and they are not more expensive, right? PWRs have extra parts, so they are more expensive. Control rods absorb neutrons, and that's what's going to stop the chain reaction. Now, this one, there's 2 questions about this, and it's something that I've not covered in great detail. So a vacuum forms in the condenser, causing steam to move from the reactor to the turbine. So this is a very good nuclear question, and you'll see me use these a lot, where there's 2 blanks, and you have to fill them in. And you'll see that a lot in the nuclear industry, and you'll see it a lot on my tests as well, just getting you ready for that. So a scram is defined as a sudden insertion of all control rods, which stops the chain reaction. A LOCA is a loss of coolant accident, where we have a leak and water is getting out of the reactor. So PWR has a higher pressure because the steam will boil at a higher temperature then. So it's going to keep all that steam in the liquid phase. So boiling and pressurized water reactors operate around the same temperature, around 550 degrees Fahrenheit, but in a PWR, they keep it water solid. So the chemical control system in a PWR is going to clean the reactor coolant, and it's going to keep the water borated. So we talked about that in that chapter. The steam generator is going to take heat away from the reactor and send it to the turbine. And the pressurizer is going to maintain pressure all the time under normal conditions. So a CANDU is a Canadian deuterium uranium plant, which is a little bit different than the BWR that GE makes, but there are less videos available with really good tours of the US reactors just because of security concerns. So that CANDU is a heavy water reactor, but we do not have any heavy water reactors in the United States. All of ours are light water reactors, and light water is what you get out of the tap. Heavy water is something that you have to make out of deuterium, which is a isotope of hydrogen. So control rods are safer when they're coming in from the top in a PWR just because it's gravity assisted. So on a BWR, they're coming in from the bottom. So why would we do that? Because there's a steam separator and a steam dryer on top of the reactor. So we can't have the control rods go through those 2 components. So defense in depth, this makes the most sense to me with a sports analogy. Not everybody's going to line up right on the line of scrimmage. You're going to have like 3 rows of defenders in any sport. You know, football is the one that's starting now. And we do the same thing at the nuclear plant. So we have multiple layers, which you'll see in the I believe, test number 3 section, just how many layers of defense we have to keep water on the reactor. So draw and label. So make sure you follow both those steps, right? Label it, draw it, tell me what everything is. Make sure for the BWR, the control rods are coming in from the bottom. And this is just the picture out of the PowerPoint, which should look a lot like your picture. What's the ultimate heat sink at a power plant? It's going to be whatever the water source is nearby. So some plants have the ocean, some plants have a river, some plants have a man-made lake even. So that's going to be the heat sink. And then where does the heat go? It's going to go either back into a large water source, or if it's a small water source, it's going to have cooling towers for it to go up into the air. Then here's the second part of that question. So what force moves steam from the reactor to the turbine? We're going to have a vacuum in the condenser, and nature does not like vacuums. So we have 1,000 pounds of pressure in our reactor. and we see a vacuum in the condenser, well, that 1,000 pounds is going to do everything it can to get to that vacuum. And one of the things that it has to do to get there is to spin the turbine. So that's what's actually moving the steam from the reactor to the turbine. And you'll see the same thing like with hurricanes. The lower the pressure goes on the hurricane, the stronger the hurricane gets because it's pulling in more moisture, pulling in more thunderstorms and things like that. So all of nature works that same way, where if there's a low pressure, everything is going to go towards the low pressure. With a hurricane, everything kind of gets there at once and causes that spinning motion that's so terrifying. So draw and label a PWR. So you should have some extra components here, the pressurizer and the steam generator. Everything is very similar, especially if you compare this secondary loop to the primary loop on our BWR. But this loop has a couple of extra parts, and the control rods are coming in from the top here on the pressurized water reactor. So draw and label as many of these as you can. Everybody did the quiz. This is much easier than a normal year because you can just look at the PowerPoint and kind of go through. And we will make sure that we know what all these different pieces and parts are as we move on. So that's it for the test. Let's start looking at the PowerPoint. It's a good place for you to pause and take a break if you so desire. So let's look at control rods. Here are some different types of control rods that we have. So they're used in nuclear reactors to control the fission rate. So how often the atom splits. When I talk about fission, I'm talking about splitting the atom. We will not be talking about fusion very much, which is what the sun does. So they can be made of different elements that absorb neutrons. So boron is a really good one. We've already talked about boric acid and things like that. So we can put solid boron in the control rods, not a boric acid liquid type thing, but we'll have solid boron in our control rods. We could also use silver, indium, cadmium, and some other isotopes to be able to absorb neutrons. So hafnium is another really good one. So both types of plants use control rods, and they can make small changes in power, or they are also our emergency brake. So if we need to put them all in at once, we call that a scram. So for a modern reactor, it takes about 2 seconds for 90% reduction, and that there's still going to be heat in there. So it's going to be a slow process, right? It's going to take a little bit of time. And different plants are going to have different numbers of control rods. BWR at Brunswick has 137 control rods, and the PWR at Harris has 52 control rods. So BWR, all these control rods are treated the same, but at Harris, they actually have two different types. They have clusters, and they can be inserted or withdrawn as a group. So they have less control rods, but they're going to have the same amount. Again, just like with the fuel, they're going to have roughly the same amount of stopping power. So in both plants, they have about 12 feet of travel, 144 inches, and they can move different amounts from 5/8 of an inch to 4 inches. So to move this 144 inches, 5/8 of an inch at a time would take a pretty long time. So what are we going to make them out of? So for a PWR, they like to use silver, indium, and cadmium as their neutron absorber. In our PWRs, we use boron carbide, which is a solid this time. So that way it can't melt or anything like that and cause problems, leak out of the control rod. So we do like to use boron carbide. So that the physical blade of the control rod is going to be made of, having a hard time here. So the physical blade of the control rod can be made of stainless steel or different alloys like nickel, chromium, iron. Zircaloy is another alloy that's frequently used in the reactor vessel. Basically things that can stand up to all the problems that the reactor is going to pelt them with. So it's got reactor pressure and temperature. The reactor is running, 1,000 to 2,000 pounds, 550 degrees. So it can't give in to either one of those, right? It's going to have to be really strong, and it's going to have to be heat resistant. We don't want something that becomes radioactive. So the last thing we want is our control rods to become activated, is what it's called. So when it is in there, it's getting hit with all those neutrons and everything else. It can itself become radioactive. A plant I was at up in New Jersey, they actually had this problem. The first time they took their control rods out, they were very, very radioactive because one bolt up near the top had become activated from being in the reactor. So they actually had to cut that piece of the control rod out and leave it in the fuel pool. And it was still in there when I was working there, 40 years later. So we don't want anything in there that can become activated, is what it's called. So it gets hit with radiation and it becomes radioactive itself. And it has to be something that absorbs neutrons, otherwise it's not going to be worthwhile. So the stainless steel and these alloys are not going to necessarily absorb neutrons. It's the boron or the silver indium cadmium that's going to be what's actually absorbing the neutrons. So a PWR can passively scram, and we talked about this on the test there. If I turn the electricity off, those things are just going to fall into the reactor because we have gravity there. You're basically using a magnet to hold it up. So if that electricity is lost to the magnet, it's just going to fall down into the reactor vessel, and that's called passively scram. The boiling water reactor, it's coming in from the bottom. So if everything goes away, that we have to make sure those control rods still go in, but we can't just do that passively with gravity. We're going to have to use hydraulics. So HCU is hydraulic control unit. So we have a pressurized tank down there that is constantly maintained up above 1,000 pounds, and it's going to push the control rods into the reactor when they're needed. So here we are, we're looking down from the top at a PWR rod. So the ones that we were looking at earlier that looked like a little cruciform, a little X, those are BWR rods, right? See, these are very simple in design. They've cut away a little bit so you can see the rods that are inside there, but all these control rods are relatively simple, kind of like an X design. So when we look here, we see tons of little teeth kind of reaching down through the fuel. So all these are the individual rods that we saw on the cutaway there, and this is cutaway as well, but this is actually going down into the fuel bundle. And here we are looking at it from the top. You can see all these pink things are the rods. So they're going to go about 12 feet into our screen, and they're going to be down in mixed with the fuel kind of. So at a PWR, we're going to have two different types of control rods. At a BWR, all the rods are the same. At our PWR, our pressurized water reactor, we're going to have control rods and we're going to have shutdown rods. So this is our brakes, and this is going to be our emergency brake. So the shutdown bank is basically going to be fully withdrawn at the beginning, and then we'll use these control rods to control the power. So you can also see that they're grouped together, so we can move these all simultaneously. In a PWR, those are the ones that move the much smaller amount, closer to 5/8 of an inch. So if I'm only moving them 5/8 of an inch and I have 144 inches to go, it's going to be a little bit easier to move either 4, 5, or 8 of these control rods at once instead of just moving one at a time like we do in a BWR, where they move a much greater distance. They move about 4 inches a shot. So here are a picture of some hydraulic control units that we're actually using in the power plant. We've got a nitrogen tank next to a water tank, and that nitrogen pressure is going to push in and push this water up, and that water will go underneath the control rod and push that control rod into the reactor if we need to scram. So all the time, I said we have 137. You can see about 20 here, and there's 8 rows of these. So we have several rows of these hydraulic control units. You can see that they are contaminated. Right here is a contaminated rope. That's why they're standing over here kind of far away from it, right? They're keeping their dose as low as reasonably achievable. They're not standing right up against the rope and against this radioactive source. They're giving it a good bit. And right there you can see a floor drain, and you can see it is also a contaminated area. So you don't ever want to step on those floor drains. So here is the big drawing for our PWR. I'm actually going to see if we can zoom in a little bit here. So we have the big tank outside, the CST, condensate storage tank, and that's going to hold all the water for us. And it comes over here to these 2 pumps. It's going to be very, very clean water because we have a lot. You can see this is a pretty small little device. There's going to be tons of seals and gaskets and things like that. So any debris that's in this water is going to cause a huge problem if it gets into our hydraulic system over here. So you're not responsible for understanding everything on this, but we will look very in depth and in detail at the part here to make sure that we understand the hydraulics before you actually are out in the field. And there's a hydraulics class that you'll take later in your CFCC career. So it's going through this first filter, and then here is a second filter. So we really, really, really want to make sure that no debris gets over here. And we have those 7 headers that I'm going to be asking you about. So you can see they're all going different directions. We have different color headers on here, and we'll go through all those in depth and in detail. So I know this is a lot to look at now, but again, as the time rolls on, you'll get more and more familiar with these pictures, and they will make a little bit more sense. So for Brunswick, they're just generic GE hydraulic control units. So if you've seen a rap video and you see their car go up in the air, that's hydraulics. So they're using the same thing that we are using to push our control rods in. And there's 137 of them, and they're in 4 different groups, 8 total rows. And then you can see it says 20 foot of the reactor building. That's just telling you where it is at. So instead of saying the first floor, second floor, third floor, we'll give it to you by elevation. So the 20 foot is 20 feet above sea level. So you might go to a plant out in Illinois and it'll have a 350 foot as the ground level, as to where here we're close to the coast, so our bottom floor or our ground floor is 20 feet. There's actually a few floors below 20 feet. One of them is even minus 17 feet, so 17 feet below sea level. So here are our actual valves, right? We have 2 valves here that we can control, and what's controlling them are these solenoids, and this is control rod number 2603, and you can see our GE logo there, so we know who made it. Here are, oops, here are our 7 headers. I'm going to zoom back out a little bit. And here are the headers. So the charging water header is going to keep the pressure up in the scram accumulators. So the scram accumulators are these tanks we're looking at here. So it's going to make sure that there's 14 or 1500 pounds of water pressure in these tanks and about 1,000 pounds of gas pressure over on this side. The insert and withdrawal do exactly what they say. They move the control rods during normal operations. And then we have a scram header, and that's going to push all those control rods in at once. So we aren't going to use the normal insert and withdrawal path. We're going to have a special path just to make sure that we get that water in there, or get the control rods in there as quick as possible by pushing them with water. The exhaust header is an exhaust, right? These insert and withdrawal, the water has to go somewhere. Water is not compressible. So if I try to insert the control rod, but there's water in the way, I can't move it unless I have an exhaust path. So that water is going to exhaust somewhere. And then the cooling water header does, again, exactly what it says. It cools the water. And then the drive header is going to give water to my insert and withdrawal headers. So there is the purpose for your 7 headers. And then let's take a look at this picture. So this one is one that you need to know for the test. Up here at the top is my piston. So my control rod would be up above this, right? So this is our directional control. So there's a few different things I can do here. So let's first off learn about the valves, right? So here is a bow tie, here is a bow tie. So if it's this lighter blue, that means that it's open, and this darker blue means that it's closed. So these with S's, these are solenoid valves. So they are controlled by magnets. So if the power went away, it is going to fail these in the appropriate way. And then here are our scram inlet and scram outlet, and those are pneumatic valves. They are controlled by air. So if we look back at our picture, here are our air valves. These 2 guys are our scram valves. And then 1, 2, 3, 4 are our solenoid valves. You can see they're pretty small little electrical connectors, and the valves that are in here are not gigantic. They're relatively small, but you can actually physically see those things in the power plant. So if I want to insert a control rod, we want to be really careful about withdrawing, but inserting is fine, right? That's the safe direction. If you're driving your car, you want to be really careful about pushing the gas, but if you're hitting the brake, it's more okay. You got to worry about the person behind you, but overall, it's going to be safer to slow down than it is to speed up, and it's the same case here. We don't have to worry about anybody tailgating us in the power plant. So the water is going to come in this drive header, and then it sees 2 closed valves. So if I want the control rod to go in, I'm going to open the 123 and the 121. So those 2 valves are going to go open. So now the water can go left. It comes here, and it's going to go towards the control rod because there's a lot of pressure here. It can't go this way. So it's going to push up. It's going to go through this 101 that's always open. And this is just a valve that we can control by hand. And you can actually see it on the picture. And the water is going to come in here. So we can't compress water. So there's water up above this piston as well. I need this water to go somewhere, right? I've sent the insert. Now I need to get this water out. So it needs an exhaust path. It's going to come down and go over this way. So we opened that 121 up. So it's going to see that, and it's going to go out the exhaust header. And we will use that water again. It's not going to the atmosphere, and it is contaminated water. So we have to keep it contained, but we also recycle it because there's no reason to get rid of it. So that is our insert signal, right? Just go through the drive, through the 123 up, through this one, which is always open, right? This guy's closed for now, and it's going to go underneath. And then now we need to exhaust this water that's on the top. Otherwise, our piston is not going to move. It's going to come down and find these two closed valves, but we open this one and it's going to go out the exhaust. And this is just going to be one switch in the control room that tells it to manipulate both of these little solenoid valves. So it's not something out here where I'm messing with this, right? It's just going to be a really quick and easy process. So withdraw, I really want to make sure that I don't accidentally flip that switch and withdraw the control rods. So I have kind of like a Chinese finger trap on there. If it's going to insert, it's fine. That finger trap will open up. But if I try to withdraw it, that finger trap is going to stop me from withdrawing the control rod, especially accidentally. So what I need to do is actually insert it for a second. So I'm going to send that same insert signal that we just sent, and that's going to open up the collet fingers, and it's going to let that control rod basically move in just a little bit. And that now our fingers are loose. So now we can send that withdrawal signal. So what the withdrawal signal is going to look like, our water comes here from the drive header, and it's going to go right this time. And it's going to go up above the piston and push down on it. And again, we need to exhaust this water that's on the bottom. So it's going to come out and make its way to the exhaust header, because those are the two that we need to open to actually get the water out. So please watch this again. I'm not going to beat it to death too much. I want to make sure that you understand it, but I'm trying not to repeat myself too much whenever you can re-watch the video. So if I want to scram, right, I'm not using this insert and withdrawal crap. Forget about that. I have my own dedicated scram path. So I'm going to open this one. I'm going to open this one, and that rod is going to go in. So the water is going to rush in, push underneath. This water on the top needs to exhaust, and it's going to go out this scram outlet to a tank that I have that I call the scram discharge volume, just to make it go. Here are the 4 valves that we're actually talking about, zoomed in a little bit. You can actually see the numbers on there, 121 and 123. Up here is 121 and 122. And, you know, these are the actual electrical connectors that are manipulating the valves that are down in our little box here. Here are our 2 accumulators. On the right is nitrogen, on the left is water, and this one's around 1,400 pounds. This one's around 1,000 pounds. And basically, during a scram, this will push in underneath here and pressurize it and force that control rod in. So whenever I open this scram inlet, all that nitrogen from the tank is going to rush in underneath the water, push it up and into the core, and then the scram outlet is going to come out via the scram discharge volume. And these are always pressurized, always at 1,000 pounds. Electricity is not necessary. If these things start to drift down below 1,000 pounds, the control rod panics and scrams itself. So this is a gauge that we look at every day, 137 of them, to make sure that these things aren't starting to get too far below 1,000 pounds, right? It looks like 955 PSIG is when we're starting to have problems. So now let's look at the CRD mechanisms, and here is one of the videos that I want you to watch. And again, it'll help you out a lot with understanding what we're actually looking at here. So the CRD mechanisms are giving us the motive force for moving the control rods around. So we just talked about the hydraulics in a BWR, so now we're going to look a little bit more at the electrical system in a PWR. So failure of any one mechanism isn't going to prevent the whole thing from working, right? We have 137 independent control rods. So if one thing fails, it's not going to cause all the control rods to fail. It's going to cause one control rod to fail. And certainly we better be safe enough to make sure that we can still stop in that case. So for the PRD mechanism, we're using a magnetic jack. So basically the magnet is going to pull it up out of the out of the reactor core. And if that electromagnet lets loose, it's going to cause it to drop back into the core. We have some latches, just as it pulls it up a notch, those latches will grab onto it, and those latches will let loose as well if the electricity goes away. So basically here is our rod, and it's getting pulled up. You can see some latching mechanisms here that'll grab onto it at these different intervals to keep it where we want it, unless the electricity goes away, and it'll drop back into the core. So there is a BWR control rod down in its little tube there. You can see it here pictured. The purple is our control rod guide tube. And up here is the fuel. So these control rods are currently withdrawn. And underneath here is our hydraulics that are going to be pushing them up and bringing them back out, and different things like that. There's a velocity limiter on the bottom. We already talked about this to slow the control rod down a little bit. And here is a little cross section of our actual control rod. So we're looking at it's going to go 12 feet into the screen. All these silver ones are going to be boron. And then on the tip, we have hafnium, which is much, much better at absorbing neutrons than boron is. So we use hafnium on the tips. So if it's a much better absorber, why don't we use it everywhere? The Navy actually does use it for their whole control rods because they do not refuel or replace control rods. So these hafnium tips are there's a little gap here, right? You can imagine there's 4 fuel bundles here and there's a gap. So we need a little bit more absorption in this area than we do, say, over here where there's 2 boron rods really, really close to these fuel rods. So these hafnium tips are just extra good absorbers. So just reviewing, the CRD mechanisms are what's actually moving them around. They also can quickly scram them when needed, and every control rod has its own mechanism. PWR rods are scrammed by turning off a magnet, and there's grippers and latches in there that are used to insert and withdraw them and keep them stationary. Control rod materials are going to be different based on the type of reactor, and we talked a little bit about those materials. Zircaloy is the most common one in a boiling water reactor. And there's a lot of materials you could use, but you have to be worried about how they're going to stand up to reactor temperature, pressure, and radiation. So there are the 7 headers again. So please let me know if you have any questions about that. This is a great place to take a break before we go into the nuclear fuel section. So here is our nuclear fuel video, and it'll show you how fuel is actually made. A very, very good video. So what is the fuel made out of? Uranium-235 is what is going to be our primary fuel. Unfortunately, when we're digging uranium out of the ground, we do not get that isotope very often, only about 0.7% of the time. So 99.3% of the uranium that we dig out of the ground is not a very useful fuel. So we could also make it out of thorium or plutonium. Thorium just turns into uranium once it's exposed to some neutrons, and plutonium is not something that we can dig out of the ground. It's something that we have made as humans, and its half-life is short enough that all of it that was made during the Big Bang has already decayed. So the fissionable material has to be contained in the core for 6 years. So we have to make sure that whatever material that we're making this out of can stand up to the reactor for 6 years. Control rods are closer to about 10 years before they come out. Uranium and plutonium are the most common fissile materials, which when you see fissile, think about missile. These are both really good for making missiles. And zirconium and stainless steel are 2 materials that we use to actually contain that fuel and make sure that it does not leak into the water in the core. So on the left side here, we have the fuel. You can see the new rods are the silver little dots down there at the bottom. And the old ones are the ones that are a little bit more corroded, but hopefully still pretty clean. And on the right, we have our fuel pool. And that's just where we're going to store the fuel for a few years before we can take it outside and put it in dry cask storage, which is just, a big concrete block that we sit outside and we let the wind cool it because it's not so hot that it needs to be cooled by water. So after it comes out of here, it's actually going to spend a few years over here in our fuel pool just cooling off. Before we can actually take it out of the water. If we took it straight from here out of the water, whoever is on this crane above it is going to die. So it is very dangerous stuff for a while there. You can actually see a little purple glow here as all the electrons in the form of radiation that are coming off of this hit the surrounding water. So, and they try to violate the speed of light, but the speed of light is not cool with that and slows them down instantly. And when it does that, emits a photon, which a photon is another word for light. So that creepy blue glow that's around this particular fuel rod is called the Cherenkov glow. And, on The Simpsons, it glows green. In real life, it glows purple. And I'm pretty sure to me, purple is a little bit weirder. Green is a little bit grosser. So when we're talking about the fuel bundles, they have to be orientated correctly. So we have a 515 or 500, more than 500 fuel rods in here, and we have to make sure we get the right rod in the right place, in the right orientation. So even the 90-degree turn has to be completely correct. So we have to make sure that when we put it in, see how all these are facing the center here. We can't have one of these turned around. So that's our dummy proof, is this 4 grouping of fuel bundles around a control rod is all going to be facing the same way. So they have a couple pictures in here that are wrong. You can see this guy's messed up. And Field Corps in the past and Sonic now do have a lot of fuel movers. So if you've worked on the refuel floor for a couple of years, they may want you to go up and actually move the fuel. So something else that we put in the fuel besides just uranium is a burnable poison. So we put more fuel in there than what we actually need. So what we do is put something similar to a control rod in the fuel just to slow everything down. And it takes like 3 months or something like that for us to actually burn off these poisons. So when it's talking about poisons, it's not something that would kill you, although I wouldn't recommend eating gadolinium. You put it in there just to slow the reaction down. And as neutrons hit this gadolinium, they get absorbed. So it kind of functions like a control rod and slows everything down. And it lets us run for 2 years. So as recently as 10 years ago, most of the plants only ran for about 18 months, but we've perfected, or let's not say that, we've gotten better at putting extra fuel in there and canceling out with this gadolinium, which will absorb some extra neutrons and make sure that we don't melt down while we have too much fuel in the core. You can see here a little bit of fuel damage. This is a big deal because the radioactivity is going to leak out of this thing now, and it's going to end up all over the plant and cause problems for everybody. So the coolant radioactivity is going to spike, especially if we're changing power. We're going to have a lot more noble gases everywhere, xenon and krypton, which are very hard to do anything with and can be radioactive. Our steam jet air ejectors, so all the different pieces and parts are going to have higher radiation monitors. And then we're going to have weird ratios of our xenons because the radioactive one is leaking out of the core. So this was caused by a little wire brush or something very, very small causing this. And we have to eventually shut the whole thing down and go in there and find this one rod amongst the tens of thousands of small rods, right? So there's 500 bundles, and each one of those bundles has tons and tons of these rods. So we had to go in there and actually find this one particular piece. So you can see there's some potential causes for fuel damage. So foreign material is one of the major causes. Another thing that can happen is the pellet and the clad can interact. So inside here, there are a bunch of pellets, and those pellets are, of course, going to expand and contract with heat. So one way that we could damage this rod is by having the expansions not match up. So if we heat it up very fast or cool it off very fast, it could cause one or the other to expand or contract too fast and give us a little crack. And it could also be a manufacturing defect. So whenever we get the chance to go over to GE and take a look at their fuel manufacturing facility, that will be an excellent way to see how careful they are whenever they're actually building these. So this is a huge mistake. So these things cost, millions of dollars each, and somebody's dropped them, and you can see they're bent over like that. There's no way we're going to be able to put these into the reactor. So we'll recycle as much as we can, but these are going to have to come all the way back over here to Castle Hayne, and they'll take it all apart and reuse as much as they can and put it back together and ship it back to Limerick. So the worst OE, this is nuclear fuel from the Chernobyl disaster. This is called the elephant's foot. And it is a very bad place to be, right? We sent some robots in here to take pictures, and even the robots died. So it's a very dangerous little glob of molten uranium, all kinds of different stuff. So this is exactly what we do not want to happen with our fuel. So there is the other video I want you to watch. It's coming from the ground, right? We're taking uranium out. And like I said, we get mostly uranium-238 and only a little bit of uranium-235. So the first thing that we need to do is actually change that ratio and get it up to about 5% uranium-235. So it was 0.7%, and we want it to get up to 5%. So we call enrichment. So if you heard about the centrifuges and things like that in Iran, that's what they're using to enrich their fuel. So if you spin it, the heavy things and the light things spin, separate a little bit, and you end up with this higher enrichment after spinning it a lot. And just like with the control rods, the Navy ships are also going to have a much higher enrichment with their fuel because they don't refuel. They're more likely to take the whole reactor out, literally the physical reactor out, and put a new reactor in. So they will do that once every 20 years. So they don't stop every 2 years to refuel their submarine. They just refuel it once every 20 years. And sometimes they just decommission the submarine if the cost is going to be too much. They're going to make this uranium-235, 238 mixture into pellets, and then put those pellets into rods, and then put those rods into our bundles, right? Our 10 by 10 lattice. So if whenever you all are in the classroom next in the front left corner, you can see one of these lattices. And there's 560. There we go. For some reason, this number slipped my mind. There's 560 of them at the Brunswick nuclear plant. So PWR fuel, they have about half as many bundles, but pretty much the exact same amount of uranium-235 is going to be in the core. And the control rod is going to be in yellow. The fuel is going to be in blue. So you can see the control rod is actually threading down into the fuel assembly. So it's a little bit of a different design for sure. So there you go. You can see the rod going down into the fuel bundle. So instead of having the cross with 4 fuel rods around it, you have this bundle going directly into the fuel. So here's another look at our little latches and our CRD mechanisms that are gripping onto everything there and the magnets that are holding on to it. So BWR fuel is around a 10 by 10 matrix, and PWR is about a 17 by 17. So one bundle is going to be roughly, not quite, but roughly 100 pins in here, 17 times 17, 250, something like that. So uranium-235 is the most common fuel. We breed that plutonium in the reactor, so it kind of gives us a little bit of extra bump in fuel. And in the PWR fuel, there's those empty blocks so that we can put the control rods basically into the fuel. So there'll be a fuel rod, single rod right next to a fuel control rod. And each one of those rods is more like a pencil as opposed to being a much bigger thing like it is in a BWR. So a fuel leak is going to mean that there's higher radioactive all through the plant. And this is very expensive, very costly maintenance. It's also going to cause you to get exposed more. So we really, really need to avoid that. And then we have burnable poisons in our fuel. It's another thing that we put in there. Gadolinium is a very common one. And basically it was just to get us a little bit more fuel in there so that we can make it from 18 months to 2 years. So if I put 2 years worth of fuel in there, but I didn't put anything to slow the reaction down, there's a much higher chance that I melt down the reactor. So we add these burnable poisons in. So fuel is found in 3 places: the reactor, the spent fuel pool, and then the dry cask storage outside. Uranium comes out of the ground, and plutonium-239 is going to build in over time, giving us some extra fissile material. So there is our control rod review. So please let me know if you have any questions, and I hope you have a good week.